Greetings, this is Professor Roman, and we'll continue our lectures on linear algebra. In this lecture, we're going to finish chapter 4 of my book on eigenvalues and eigenvectors. The simplest type of linear operators on a finite dimensional vector space, aside from just scalar multiples of the identity, are the operators that have a diagonal matrix representation. It would look like this. And it's relatively common to write this this way. DIAG stands for diagonal matrix with the following diagonal entries. This saves a lot of vertical space, and you will see it in other books as well. A linear operator that can be represented by a diagonal matrix is said to be diagonalizable. A matrix is diagonalizable if it's similar to a diagonal matrix, and that's consistent with the dual personality of a matrix, either as a formal array or as a linear operator. So I should probably say square matrix, but if it is similar to a diagonal matrix, then it is square. It's pretty clear that a linear operator, tau, and these are all on finite dimensional vector spaces since we're discussing matrix representations, is diagonalizable if and only if the vector space V has an ordered basis consisting entirely of eigenvectors. This basis B here, every one of the vectors in B is an eigenvector corresponding to one of these diagonal elements. An ordered basis that consists only of eigenvectors is called an Eigen Basis for the vector space, or really more appropriately for the pair V tau. V is the vector space, tau is the operator. If the spectrum of a linear operator looks like this, lambda 1 through lambda m, then we can order the eigenbasis by grouping the basis vectors for each eigenspace, in other words, for each eigenvalue together. So what we do is we take, let's say B sub k be an ordered basis for the eigenspace associated with lambda sub k, and then we can string those bases together into a basis for the entire vector space, and what we will get is a matrix representation that looks like this. This portion of the matrix representation is comes from the eigenvalue lambda 1, and so the vectors, let's say there are k of these, then the first k vectors in B are the eigenvectors that form a basis for the eigenspace associated with lambda 1. And again, this is a somewhat more convenient way to express this matrix representation. So we're simply, if tau is diagonalizable, it has a basis, an eigenbasis. We simply order the eigenvectors in the eigenbasis to collect all the eigenvectors together that correspond to a single eigenvalue. Okay. There are various simple ways to characterize diagonalizability, at least in theory. In practice, we face additional problems because obviously if an operator is diagonalizable and you can find its diagonal matrix representation, you have exposed its eigenvalues. In other words, you found the roots of the characteristic polynomial. And that, of course, as we discussed last time, is something that's not always possible to do. In fact, quite often it's not possible. We've just seen that an operator tau is diagonalizable if and only if the pair v tau has an eigenbasis. And again, by reordering that eigenbasis, we can get this type of matrix representation. But the pair v tau has an eigenbasis if and only if the direct sum of the eigenspaces is all of the vector space V. In other words, V is the direct sum of the eigenspaces. We know this is a direct sum because we know that eigenvectors associated with distinct eigenvalues are linearly independent. This holds if and only if the sum of the dimensions of these subspaces is equal to the dimension of V. So if V is n-dimensional, I guess I better add that, dimension of V equals n, then the sum of the dimensions of the eigenspaces is n. Here's a theorem that summarizes what I've just said and adds another characterization of diagonalizability. So we'll let V be an n-dimensional vector space over F, and tau is a linear operator, and here's the spectrum. Then the following are equivalent. Tau is diagonalizable. The pair v tau has an eigenbasis, in which case, by reordering the basis vectors or ordering them appropriately, tau can be represented by a diagonal matrix that looks like this. V is the direct sum of the eigenspaces of tau. The sum of the geometric multiplicities or dimensions of the eigenspaces is n, which is the dimension of V. And one more characterization. The characteristic polynomial of tau splits over F, and all of the eigenvalues are non-defective, meaning that their geometric and algebraic multiplicities are the same. We have shown, we discussed last time, that the geometric multiplicity is always less than or equal to the algebraic multiplicity. And when it is strictly less, we say that the eigenvalue is defective. Okay. So we've already discussed the fact that 1 through 4 are equivalent. For part 5, suppose first the tau is diagonalizable. Then it has a diagonal matrix representation, this here, and so the characteristic polynomial is just the product of these linear factors x minus lambda I to the power e sub I, where e sub I is therefore the algebraic multiplicity of each eigenvalue. So the sum of the algebraic multiplicities is n. Also, an earlier theorem, 422, and part 4 of this particular theorem here tells us that the sum of the geometric multiplicities is equal to n, every geometric multiplicity is less than or equal to the corresponding algebraic multiplicity, and that also sums to n, the sum of the algebraic multiplicities. So this is in fact an equality, and the sum of the geometric multiplicities equals the sum of the algebraic multiplicities. And since each geometric multiplicity is less than or equal to the corresponding algebraic multiplicity, but their sums are the same, they must in fact be equal. Conversely, if the sum of the geometric multiplicities is equal to the sum of the algebraic multiplicities, which is n, the dimension of the vector space or the degree of the characteristic polynomial, then tau is diagonalizable. So we have several ways of characterizing diagonalizability. I should point out probably that diagonalizable operators or matrices are rather rare. This is an exceptional situation. In the first place, the characteristic polynomial has to split over the base field. And so if the base field is the real numbers, we're going to run into significant problems there. If the base field is algebraically closed, then this presents no problem, such as would be the case for the complex field. But there is this issue of the non-defectiveness of the eigenvalues. Okay. If we have an eigenbasis for, let's say, a matrix A, we know that A is similar to a diagonal matrix. Call it D. With diagonal entries lambda 1 through lambda n, those are the eigenvalues that correspond to the eigenvectors in the eigenbasis. But it is of considerable interest to find the similarity matrix P that fits this equation. Since A is similar to a diagonal matrix, there must be an invertible matrix P for which D equals P inverse AP. And we want to know what P looks like. Well, the answer lies in the formula for the change of matrix representation. D is the diagonal matrix. It is the matrix representation of A with respect to the eigenbasis B. And this is the change of matrix representation formula. This is the matrix representation of A with respect to the standard basis, which is, as we have seen, just A itself. So we have D equals this matrix times A times this matrix. So this is P, the similarity matrix that brings A into diagonal form. And by definition of the change of basis matrix, its columns are the new coordinates or the new coordinate vectors of the old basis vectors. But the new basis is the standard basis. So since these vectors v1 through vn belong to Fn, their standard coordinate matrices are themselves. So we just get this. In other words, the columns of the similarity matrix are the eigenvectors in the Eigen Basis, in the appropriate order, of course. You can certainly commit this statement to memory. It's not that complicated, but I would urge you to understand, go over this argument, understand it, be able to reproduce it yourself, so that if you get a little confused, are the columns of P the eigenvectors, or are the columns of P inverse the eigenvectors? And if you can't remember which is which often happens to the best of us, reproducing this simple argument will show you. And of course, you do need to remember the change of matrix representation formula. So this was a discussion related to a matrix and how to find the similarity matrix. As to diagonalizable linear operators, tau, well, we can first compute any matrix representation, call it A, for tau, then find an Eigen Basis for A, the matrix A, and then proceed as we did here to get P. Of course, the hard part of that is finding the Eigen Basis, and because that first requires finding the eigenvalues, and we've already discussed the fact that in general that's impossible, only possible in special cases. So here's a summary. B is an eigenbasis for matrix A, and if P is the similarity matrix, then P is this matrix here, whose columns are the eigenvectors in the Eigen Basis. Examples. Excuse me. Here's a 3 by 3 matrix. Here is its characteristic polynomial, which I worked out separately, or there's a computer program actually that'll do it for you. The eigenvalue 1 has algebraic and geometric multiplicity 1. The algebraic multiplicity is just read off from this. It's the multiplicity of 1 as a root of the characteristic polynomial, and that's 1. The geometric multiplicity is less than or equal to the algebraic multiplicity, and therefore must also equal 1. For the eigenvalue 2, this is a formula, we've seen this earlier. For the dimension of the eigenspace, it's the full dimension, 3, of the vector space minus the rank of A minus 2i. This is what A minus 2i looks like. It has rank 1. And so the eigenspace is two-dimensional. Therefore, the geometric multiplicity is equal to the algebraic multiplicity too. So both of these eigenvalues are non-defective. And the sum of the geometric multiplicities is 3 characteristic polynomial splits. All the eigenvalues are non-defective. According to the previous theorem, this matrix is diagonalizable. That's quite remarkable. We've just shown that this matrix is similar to a diagonal matrix. And the argument we used here is a more or less straightforward calculation. no heavy-duty work here. So this demonstrates the power of our analysis. To find the similarity matrix, we need an eigenbasis. So we compute the kernels here that are the eigenspaces, and we get our eigenbasis here, so corresponding to the eigenvalue 1 is this eigenvector that spans or is a basis for that eigenspace. So that goes as the first column of the similarity matrix. The eigenspace associated with lambda equals 2 is two-dimensional. Here is our basis. And so these two vectors form the other two columns of the similarity matrix. And so when we apply the similarity matrix to A in this form, we get a diagonal matrix with the eigenvalues on the diagonal. These are not the only choice for eigenbasis. You can multiply one of these by a scalar, for example. So you could, say, replace v1 by 2v1, and that would alter the similarity matrix, but not the diagonal representation, because it must have the same, it has the eigenvalues on the diagonal. The only variation you're allowed here is in the order of the eigenvalues. Here's another 3x3 matrix. This has distinct eigenvalues, 3 distinct eigenvalues, and you can check that by, well, you can compute the characteristic polynomial, but you can notice that this is an upper triangular matrix. The eigenvalues are on the diagonal here, and they're distinct. Therefore, each of the 3 eigenvalues is non-defective because their geometric multiplicity and algebraic multiplicities are equal to 1 in each case. So we can write F3 as the direct sum of the 3 eigenspaces, and that tells us that this matrix is diagonalizable. And you can compute the similarity matrix. I left that for you to do as practice. Here's a matrix. This is the characteristic polynomial. The eigenvalue 2 has algebraic multiplicity 2. Eigenvalue 3 has algebraic multiplicity 1. So the eigenvalue lambda equals 3 is non-defective. However, when we compute the geometric multiplicity of the other eigenvalue, lambda equals 2, the dimension of the kernel of, I switched this around for some reason. It's not usually the way I do these things, so I'll just change that in the book. A minus 2i. Doesn't make any difference because we're just looking for the dimension of the eigenspace, and these two will have the same dimension, eigenspace dimension. Anyway, it's the dimension of V minus the rank of A minus 2i, and this is A minus 2i, or 2i minus A. And so this geometric multiplicity is 1, but the algebraic multiplicity is 2. So this eigenvalue is defective. And so this matrix is not similar to a diagonal matrix. Again, this reveals the power of this analysis. We were able to show that there cannot be any matrix, invertible matrix P, such that this is diagonal without actually, without showing that directly, which would be quite a chore.